In this lesson, we're going to be taking a look at a topic known as optimal values. This may be a review. Some or all of this may be review for you, or much of this might be new for you, depending on your background from the grade 10 course. I'm quite confident that this first part will be review. And the idea, first of all, let's talk about a quadratic function or a quadratic relation. We know that the graph of that is going to be a parabola of some sort. And depending on whether that graph opens up or opens down, that's going to tell us whether or not the vertex is located at the lowest point, which we call a minimum, or the highest point, which we call a maximum. Regardless of whether or not it's a minimum or a maximum, this notion of the extreme point, either the very lowest point or the very highest point, they get lumped together into a single term known as the optimal value. So the optimal value represents either the lowest point on our parabola or the highest point on our parabola. That lowest point or that highest point, as you'll notice from the graphs, those correspond to the location of the vertex. And so if you have an equation in vertex form, then you have the easiest access to the optimal value. The optimal value itself is actually the y-coordinate of the vertex. So if we think of the location of the vertex as an xy, it's actually the optimal value in the y value. When we talk, because it's a value, let's actually highlight that. Optimal values, that's a number. When we talk about a value, we're talking about a number. And so we're talking about what is the number that represents either the lowest or the highest point on your parabola. And that number is the y-coordinate. So if you've got vertex form, just read it, and this should be entirely review to you. You should be familiar with vertex form. Another option you have is to convert your quadratic relation into factored form, or if you're lucky, it's actually given to you in factored form. This is something that is likely review as well. This actually is probably the first way that you found the vertex when you first started studying quadratic relations. You would find factored form, you would read the zeros from factored form, and then you would use the notion of symmetry, the fact that the two zeros are on either side of the vertex. If I go back to my example here, let me just put dots where the zeros are on this blue parabola, and then halfway between those two zeros is what's known as the axis of symmetry. And so it's got the word symmetry built right into it. So the midpoint of those two zeros is actually going to find the axis of symmetry, and then the axis of symmetry helps you find the vertex. And once you know the x-coordinate of the vertex, you can find the y-coordinate of the vertex. So we use the symmetry to find the midpoint of the two zeros. That finds for us the x-coordinate of the vertex. And then we take that x-coordinate of the vertex and we sub it into our equation. And the result is going to be the y-coordinate of the vertex. So vertex form is the easiest possible start. Factored form is the next easiest possible start. Or you might get a quadratic relation in standard form. Now you have a couple of options here. Well, three options to be more correct. One of them, factored form, we just talked about. Now I'm going to put a question mark next to that because you'll notice that I say here, if possible. It's not always possible to factor a quadratic equation. A quadratic equation might have no zeros in it whatsoever. It is also possible to use an algebraic technique called completing the square. And it's possible that this is review for you. You probably covered this in your grade 10 course, but there are some exceptions to that where there's a good reason why you might not have covered that in your grade 10 course. If you complete the square, this will always work. You can always complete the square to find vertex form. The algebra can get a little bit gnarly depending on the different coefficients in your quadratic equation, your a, b, and c, but in general, you can always do this. And then another technique is known as partial factoring, which we're going to look at here. I figure this is the least likely to be review, but for some of you, this will be review. So I'm going to go through an example of all three here just to make sure that this is clearly illustrated. Let's start with the simpler ones, which is determining the optimal value of this quadratic in vertex form and determining the optimal value of this quadratic in standard form, but I chose something that was factorable. So for part A, we can actually do this by what's known as inspection. All of the algebra is done for us. So all we actually have to do is to read directly from this that the vertex is located at coordinates -3, 5. And so the optimal value is 5. So the optimal value is the number associated with the y coordinate. Now in this case, we can see that this parabola opens down because it has a negative leading coefficient. And so you could add this extra information, or sometimes you're asked to identify is the optimal value a maximum or a minimum. And in this case, because we have a parabola which opens down, the vertex would be at the top of the parabola, which means this optimal value is a maximum. Now we can't do this second one by inspection. We're going to have to do a little bit of algebra on it. And so we're going to use our, it's not a shortcut, it's just a mnemonic technique. It helps us organize our information. MAN. Our multiplication comes from the first and last, so that's going to be, I need two numbers that multiply to -30. We use the middle number for the addition, so I need two numbers that multiply to -30 and also add to +13. Those two numbers are +15 and -2. Now you could use decomposition here, and that is the more typical way to do it, but you can also use, there's a shortcut that you can use here, which is once you've identified your two numbers, take the leading coefficient, which is 3, and use that to make a couple of fractions here. Now it's important that you reduce these fractions if possible. So -2/3 is already reduced, but 15/3 is actually the same as 5/1. And then you associate an x value with the denominator and you read from the bottom up. And so in factored form, this becomes x plus 5, reading from the bottom up. And the second factor is 3x minus 2. So now I have this in factored form, and from here I can actually read the zeros basically by inspection. The zeros are going to occur when x plus 5 equals 0 or x equals -5. And then another 0 is going to occur, and you might need to write this one out, and there's nothing wrong with that. When does 3x minus 2 equal 0? That occurs when 3x equals 2 or x equals 2/3. So my zeros occur at -5 and +2/3. Now I'm going to make use of the idea that the zeros are symmetric around the axis of symmetry. And the axis of symmetry represents the x-coordinate of the vertex. So I can actually just add those two zeros together. So it's going to be -5 plus 2/3, and then I find the midpoint, which is divide that by 2. This divide by 2, I'm actually going to put out in front as a multiply by 1/2 because I'm dealing with fractions. And because I need a denominator of 3 in the numerator, so I need a common denominator to combine -5 and 2/3, I'm going to change -5 into -15/3 plus 2/3. So I end up with 1/2 times -13/3. And so the midpoint, you can see this is not trivial. Depending on your work with fractions, we end up with -13/6. is kind of an awkward location for the x-coordinate of the vertex. And now to find the y-coordinate of the vertex, we're going to sub that x-coordinate into our equation. So the y-coordinate of the vertex, we could go all the way back to the original. I think it's actually going to be easier if we work from factored form here. So instead of x plus 5, I'm going to put negative 13 over 6 plus 5. And instead of 3x plus, is it 3x plus 2 or 3x minus 2? It's 3x minus 2. So that's going to become 3 times negative 13 over 6 minus 2. And we're going to have to do some simplifying here. In the first bracket, we just need a common denominator of 6. So that's going to be negative 13 over 6. And then that's going to become plus 30 over 6. So I'll be able to simplify that first bracket in a moment. And then this second bracket, hopefully you recognize that 3 goes into 3 once and goes into 6 twice. So that first term in the second bracket becomes negative 13 over 2. And so I need a common denominator of 2. So I'm going to change 2 over 1. I'm going to change it into 4 over 2. And so combining these, negative 13 plus 30 is positive 17 all over 6. Negative 13 minus 4 is negative 17 over 4. And now I end up with my final little bit of arithmetic to do here. I've kind of, 17 times 17, let's see. I believe that's going to be negative 289 over 4 times 6 is 24. So this is not trivial just from a fractional arithmetic point of view, but you need to be prepared for this. Everything I did here, other than the 17 times 17, kind of just popped into my head there. You would use a calculator for that just to make sure, and I'm actually not so confident. I'm just going to double check. Let's see, 17 times 10 is 170, plus another 70 is 240, plus 49 is negative 289. And so my optimal value, remember we're interested in the y-coordinate of the vertex, so my optimal value is negative 289 over 24. If this were a word problem, you would probably convert that to a decimal, because if we're talking about distance or speed or time or something like that, negative 289 over 24 is not a particularly useful number. But mathematically, it's very useful because it is an exact value. And let's move on to some other techniques. Now, I've put this as a blue background in class. That normally means you don't have to copy it down, because for some of you, this would be review. But if it's not review, you should consider adding this into your notes. I talked about how we use symmetry on factored form to find the axis of symmetry. Same kind of thing we're going to do here. It's just that we're not going to use the zeros. And the reason is because sometimes, and I've illustrated this with a graph below, sometimes you have a parabola that actually doesn't cross the x-axis. So you don't have the choice to use zeros. You don't have the option to factor it. But on every parabola, you can always find pairs of points that are symmetric. And hopefully that's quite clear just by looking at it. The 2 points that I've labeled here are symmetric on either side of the axis of symmetry. Now, the thing that's particularly nice about the points that I've chosen here is that one of them is the y-intercept, which is a very easy point to find. No matter which form you have of a quadratic equation, the y-intercept is relatively easy. And if we're going to use this method known as partial factoring, we're going to be using standard form. And so you can just read the y-intercept off of standard form. That's the C parameter. So we're going to determine 2 points that have the same y value. We're going to start with the y-intercept as our first choice. And then we're going to find the point that matches it on the other side of the axis of symmetry. If I can find those 2 points, then I can use symmetry. I can find the midpoint of those 2 points to find the axis of symmetry. And once I have found the axis of symmetry, Now I can find the y-coordinate of the vertex, and that is my optimal value. These steps 2 and 3 are the exact same steps that we used in factored form, where we found the x-coordinate of the vertex, and then we subbed into the equation to find the y-coordinate of the vertex. So the only thing that's different with partial factoring is finding the matching point. So let's do an example on that. Those are a very condensed version of those 3 steps off to the right there, just to remind us. You can see that this graph clearly does not have zeros. It's not factorable. And so what we're going to try to do is, based off of the y-intercept, we're going to find the corresponding matching point. Now we can see that that occurs at x equals 2 from the graph, but we're going to pretend that the graph was not provided. I just added this graph in to illustrate this. I didn't mention it on the previous examples. Hopefully you did anyway. But if you're doing this as a lesson, you should pause now and you should try this one on your own. So what I'm going to do, first of all, is identify the y-intercept. Now, if for some reason you ever forget that the y-intercept is simply, in standard form, it's just the number on the end here, remember that another way, and this works for any graph, the way that you find the y-intercept is you set x equal to 0. And you can see from my equation, if I set x equal to 0, then this whole thing turns to 0, this whole thing turns to 0, and of course, I am left with y equals 1. That's my y-intercept. Now, normally you do that in your head if you needed to, or you would just remember that's what standard form gives you. So that means I have a point, the y-intercept has coordinates x equals 0, y equals 1. And our matching point has coordinates, well, we don't know what the x-coordinate is yet, but we know it has a y-coordinate of 1. So what we're going to do, and actually, you know what? I think I'm going to, instead of just writing x there, I'm going to put xm, which is the x-coordinate of the matching point. So I'm going to set the y value equal to 1 in my equation, and I'm going to use that to find xm, the matching point's x-coordinate. So what is our equation? Y equals, so instead of y equals, I'm going to say 1 equals 2/3 x squared minus 4/3 x plus 1. And the reason why this is such a useful technique to understand is, notice that by choosing that very specific y-intercept, I've actually set this up to turn into a much easier equation to solve, because I can subtract 1 from both sides. So remember, we got the y-intercept from this plus 1, which means when we set the y value to be equal to the y-intercept, those two are equal, they go away. We end up with 2/3 x squared minus 4/3 x. And this is actually very easy to factor. And we want to factor it because we've got a 0 on this side. So I'm going to just take out the x as a factor. There's more I could do there, but this is sufficient. And if you're wondering, well, should I try to take out the fraction as well? Why don't you take out the x first and then see what's left behind and decide if that's enough? Now, this is not factored form of the original quadratic equation because we modified it. We took out those 1's. But this is a different equation in factored form, and the rules for solving this are the same. I've got two factors, x and this thing in the brackets, multiplied together, and that's equal to 0. The only way that can happen is when x equals 0, or when 2/3 x minus 4/3 equals 0. Now, this x equals 0, that is where the y-intercept occurs. And so this other one must be where the x of the matching point occurs. Now, there's a couple of ways that you could solve this. You could isolate it, so I'm going to write 2/3 x equals 4/3, so I've isolated the variable. I'm just going to multiply through. I'm going to multiply everything by 3, and that's going to get rid of those fractions. So 2/3 x times 3 just turns into 2x. 4/3 times 3 just turns into 4. And then divide both sides by 2, and I end up with x equals 2. And so this is the, where's my undo? So this is the matching x-coordinate. The matching x-coordinate to the y-intercept. And now that I know that, I'm going to sub that in. So I'm going to sub x equal 2. Actually, I'm sorry, we're not quite ready to sub yet. We need to find the x-coordinate of the vertex. So the x-coordinate of the vertex is the midpoint of these two matching points, these symmetric points. So one of them occurred at x equals 0. The other one occurred at x equal 2. Divide that by 2, and I end up with 1. And so the y-coordinate of the vertex we find by subbing in x equal 1 into our original equation, 2/3 x squared minus 4/3 x plus 1. So instead of 2/3 x squared, it's going to be 2/3 times 1 squared minus 4/3 times, instead of x, I'm going to replace that with 1, and then plus 1. Now, this being 1 makes that about as easy as it could be, because 1 squared is just 1, so this first term is 2/3. 4/3 times 1 is still 4/3, but that's with a negative sign in front. And then I could write this as plus 1, but I need to add all of these things together, and they have denominators of 3. So I might as well, instead of writing this as plus 1, I'm going to actually write that as plus 3/3. Because essentially I took this 1/1, and I multiplied numerator and denominator by 3 to give it a common denominator. And now that I've done that, 2/3 minus 4/3 is negative 2/3, plus 3/3 is positive 1/3. And so therefore, in this case, the optimal value is 1/3. And let's go up and take a look at our graph. Since it was provided, does 1/3 make sense with the scale here? We wouldn't be able to reliably read that from this, but 1/3 seems to make sense. And that would be, in this case, a minimum. Now, the question didn't ask for this, but I'm just pointing it out to you. All right, the third technique, which we haven't looked at yet, is the idea of completing the square. And you've probably noticed that I'm forcing a lot of fractions into this particular lesson, so we're going to continue working that way. This is a complex trinomial because of the presence of that. There's a number other than 1 in front of the leading x squared term. So the first thing I need to do is factor that 3 out of the first 2 terms only. So 3x squared divided by 3 is x squared. 2x divided by 3 is 2/3 x. And then that minus 11 is unchanged and is not in the bracket. I don't factor it. It's just there on its own. Now I take, let me take a moment here just to point out, I take this, oh no, I need to write the next line. I'm sorry. It'll be easier if I do it underneath. So I'm going to rewrite x squared plus 2/3 x. You could even write this extra stuff out on the side there. We're not changing the 11. I take 2/3 and I divide it by 2. But dividing something by 2 is the same as multiplying something by 1/2. So I take 2/3 multiplied by 1/2. 2 divides out with 2, and I actually end up with 1/3. Then I take 1/3 and I square it. So this becomes plus 1/9, and this becomes minus 1/9, because I can't introduce that 1/9 out of thin air, so I have to immediately subtract 1/9. It is important, though, that the plus comes first and then the subtraction. Then I will complete the square, the reason I did this was to make a perfect square trinomial. So those first three terms in the bracket, that is my perfect square trinomial. That's actually x plus 1/3 all squared. The 1/3 comes from here, and the plus comes from this plus right there. That's how you know if it's a plus or a minus. Then I have minus 1/9, and still waiting outside for its chance to actually join in the fun is that -11. I'm going to expand this 3 into the bracket, or distribute that 3 into the bracket. I get 3 times x plus 1/3 all squared. 3 times -1/9 is actually -1/3. And then I'm going to take this 11/1 and also give it a denominator of 3, and that becomes -33/3. And so we end up with our final answer in vertex form. That becomes -34/3. And remember, it is the y-coordinate, so this has a vertex at -1/3, -34/3, and the optimal value is the y-coordinate of the vertex. So the optimal value is -34/3. And for our final example, just to show you, although I was very heavily emphasizing fractions in this lesson, you can also sometimes use decimals. The important thing is, if you're going to work with decimals, they have to be what are known as terminating decimals. And I'll show you what that means in just a moment as soon as I start my steps here. I have to factor out that leading 5 from the first two terms. That becomes x squared plus 8/5x minus 3. But here I said it's okay if we work with decimals. And the reason is, if you do 8 divided by 5, what you actually find is that 8 divided by 5 is 1.6. And that is a terminating decimal. We didn't have to do any rounding, and it doesn't go on to an infinite repeating number of digits. So in this case, it's perfectly fine to use decimals. It's not my preference, but I'll never criticize you for doing it. Then I take 5x squared plus 1.6x. Then I take half of 1.6. Well, half of 1.6 is 0.8. And then 0.8 squared is going to be plus 0.64. And then immediately I subtract 0.64. Minus 3 on the outside equals 5 bracket. The reason why we completed the square was to make these first 3 terms, which makes a perfect square. So that's going to be x plus 0.8 all squared minus 0.64, and then outside minus 3. I'm going to distribute this 5 into my bracket. 5 times x plus 0.8 all squared. 5 times -0.64 is -3.2. And then now the -3 can be simplified together with the -3.2, giving us our vertex form. That's -6.2. We can read the vertex from that. It occurs at -0.8, -6.2. And that y value tells us our optimal value, which is -6.2. And that is the end of this lesson. I just want to point out, this is the work that I've assigned as of the writing of this lesson. None of these questions from your textbook actually ask for partial factoring, so I've just denoted a couple that I really want you to try using partial factoring on. In most circumstances, I will never require that, but it is a technique that you should learn, and in the off chance that I ask you to do a question by partial factoring, you are responsible for it, so you do need to learn how to apply that technique.